Hello, welcome to Group 3's project presentation. Our question asks, find the volume common to two intersecting cylinders, each with radius r, if the axes of the cylinders intersect at right angles. Now at first this might seem complicated because we are taking a volume of a 3D object in which the solid common to the two cylinders isn't so clear. Now here is what is meant by two intersecting cylinders with the same radius. Now, if the intersections happen at right angles, we should expect our image to look somewhat like this. Now, the area common between the two cylinders can be shown in this shaded region. Let's make it a little simpler. Instead of an isometric view, let's try a fixed view, as in the top view. So we can see here at the top view, it is very obvious to know that a cylinder would resemble a rectangle. Two intersecting rectangles at 90 degrees would give a cross-section of a square. We can represent the area common between the two cylinders as this figure here. And it is very important to see at any cut we will get a square. This is due to the fact that each of the cylinders have equal radius r, which means each side of the cut will be the diameter. Since each cylinder is the same, we can denote both sides as 2a. So since we know that the top view resembles a cross-section in which is a square, where both sides are equal, we can find those sides by showing the isometric view in which we take any cut at the height of y, starting from the center, and then we also know the radius at that point. And then our third part of this triangle will be A. And as you can see, the side of the approximating slab will be 2A, as denoted up here. So R is the constant that we were given in the question, and Y will be the variable in which, at whatever cut, will always be changing. And we can find A by the Pythagorean theorem. Now let's explain why we're using cross-sectional slab to find the volume common to the two cylinders. Just a reminder, we can use an integral to find the volume under any function on the xy plane, in which we add up infinitely many rectangles with height equal to f of x and width of an infinitesimal size delta x. Now if we set up our integral, our bounds will be set from a to b with respect to dx. Now, for any 3D solid, we can use a similar idea, which is using cross-sectional slabs. For a cube, the cross-sectional cut at any point will be a square, and because of that, we can find the volume of the solid by considering the volume of the cross-sectional slab, which is shown here. Considering the fact that the slab will have an infinitesimal thickness, just as shown in our xy planes function of the infinitesimal width, our volume of the cross-section will be equal to the length times the width times the instantaneous height. Now for our object common to the two cylinders, it has, as previously stated, a cross-section equal to a square. However, the length and width of the square are always changing depending on what your cut is. Now we have previously solved for length and width to both equal to a, where a is equal to the square root of r squared minus y squared.
this means our volume of our cross-section will equal 2a times 2a times the instantaneous height. Or we can write this as 2a squared delta y. To finalize my point, I'd like to show the volume of the cross-section that we've previously solved, and now we're going to find the volume of the solid by taking the integral of our approximation, where the lower bound and the upper bound will be denoted as negative r to r. Interesting. So why is it that our bounds are from negative r to r? Well, it's plain to see when we set up our previous diagram of our cross-sectional cut at any height y. Now, if we set our height of our cross-sectional slab equal to the radius, that is, raise the cross-section all the way to the top of the cylinder, we will have our radius equaling to our height y.
So the volume of a cross-sectional slab is given by length times width times height. Where the length and the width are 2a, and the height is given by delta y because that is the thickness of our cross-sectional slab. Now if we clean things up a bit, as Joey said earlier, a equals the square root of r squared minus y squared. So we can substitute that in. Now we can simplify. That is the equation of the volume of our cross-sectional slab. As Joey stated earlier, the volume of the solid is given by the integral from negative r to r of VCS. And now that we know what VCS is, we can plug that in. Now we can actually pull out the 4. Now we can take the integral. R is just a constant, so all we'll be doing is adding a y to that, and y will become y cubed over 3 from negative r to r. Now we can actually evaluate via the bounds. Now, if we add like terms and put everything over a common denominator, we can simplify. And now that we have everything simplified, we can get the answer. So the volume of our solid